This is a look at Kirchhoff's laws. Kirchhoff's laws deal with conservation of energy and conservation of charge in an electrical circuit. They're also a method that can be used to solve for currents and potential differences in a circuit. I'm going to start by looking at the circuit shown here, and this is the circuit being solved using the equivalent resistant method to get the currents and potential differences for each of the resistors. The first of Kirchhoff's laws is his voltage or loop law, and this says when you go around a circuit, the potential differences have to add up to zero, and this happens when a battery or another power source adds voltage to the current running through the circuit, and then every load or resistor takes that voltage away. So here I have a battery adding volts, and then 3 resistors taking volts away, and the voltage added has to be equal to the voltage taken going around this loop. So for this circuit shown here, there's 2 possible loops that current can go around. The orange loop, which is the loop on the left, and the larger loop, which is the blue loop. If I start at the orange loop coming out of the battery is going to give 12 volts. So if I'm here before going through the first resistor, there's 12 volts that the current is carrying. And then this resistor is going to take 6 volts. So there's 6 volts dropped and 6 volts remaining. Some of the current will continue along the orange loop and go through the 3 ohm resistor, where it drops an additional 6 volts. So in this resistor, it goes from 6 volts to 0 volts, and then it goes back to the battery. So if I follow this loop, I have plus 12 volts, minus 6, minus 6 here, and that adds to 0. So Kirchhoff's law works for that loop. Now in the circuit, there's another possible path or loop, and that's the outside one. So for the blue loop, the battery adds 12 volts. It gets here again to the 2 ohm resistor where it enters with 12 volts and leaves with 6 volts. So it drops 6 volts there. And then it goes to the outer loop to the 6 ohm resistor where it's going to drop 6 volts and then go back to the battery with 0 volts. So in both cases, both the orange loop, which is the loop on the left, and the outer loop, which is the blue loop, the voltages add to 0 for each path that current can take. The other law is Kirchhoff's current or node law, and this looks at a junction point or node in a circuit. This one just says that the amount of charge flowing in per unit time, which is current, has to equal the current flowing out. So here I have current I1 flowing in, which has to be equal to I2 and I3 flowing out. Going back to the same circuit for the node law, there's 2 nodes in the circuit. So this first branch up here, current's going to enter with 3 amps, and it can either go down, where it's going to carry 2 amps, or it can go to the right, where it can carry 1 amp. So in that case, the current in 3 amps equals the current out, which is 2 amps, plus 1 amp. The current then recombines at the blue node down here. So there's 2 amps going in from up top, 1 amp coming in from the right, and then leaving is the battery current, which is 3 amps. So for both nodes, Kirchhoff's loop law is satisfied. The first example here is one that can be pretty easily solved using the equivalent circuit method and working backwards, but I'm going to solve it here using Kirchhoff's laws. And I'm solving for 3 unknown currents: the current through the 2 ohm resistor, which I'm calling I1, the 3 ohm resistor, which is I2, and the 6 ohm resistor, which is I3. Now, the first law I'm going to use is going to be the current or node law, and I'm going to choose this node right here when the current splits. So for this node, I have the current in equals the current out. I have I1 going in, and then I2 plus I3 going out. And these are 3 unknown currents, so I'm ultimately going to need 3 equations, and this equation here is one of them. Here I wrote the node equation in a form where I have variable 1 minus variable 2 minus variable 3 equals 0. And this is so that later, when I have the 3 equations, I can solve it by plugging it into a solver like polysymult on the TI-84 calculator. So that's my node equation. I want 2 more equations. So in this case, I'm going to use the loop laws. The first loop I'm going to do goes through the 2 ohm resistor, and then it's going to go up through the 3 ohm resistor back to the battery. So that red loop is a possible loop that current can take through the circuit. So I'm going to go around the loop. The battery first supplies 24 volts, and then it gets to the 2 ohm resistor, where Ohm's law says voltage is IR. So the voltage dropped there is going to be negative 2 times I1. Then it goes up to the 3 ohm resistor, and again using Ohm's law, it's going to drop a voltage of 3 times I2. And the result of that, because now we're going back to the battery, has to be 0. And again, I'm going to rearrange this in a form that I can give to a solver, and it'll give me the answer quickly. Okay, and that turns into that. So I need one more equation, because I have 3 unknown currents, and in this case, I'm going to do a loop where it goes through the 2 ohm resistor, and in this case, I'm going to go down to the 6 ohm resistor, and then again back to the battery. So the top loop there was a possible path. This is another possible path for current. For this loop, current's going to come out of the battery and gain again 24 volts. And then, just like the other loop, it does have to pass through the 2 ohm resistor, so it loses 2 times I of voltage, because voltage is resistance times current. Now it goes through the 6 ohm resistor, where that's going to be 6 times I3, and goes back to the battery, so that equals 0. And I can rewrite the equation like that. And this is a case where I can plug it into a solver, such as polysimult. And I get those currents there. I get 6, 4, and 2. I can go ahead and double check. But this node here, I have 6 amps going in, 4 coming out on top, 2 coming out on the bottom. So Kirchhoff's current law is satisfied there. If I use voltage, this is 12 volts. The 6 ohm resistor drops 12 volts. This drops 12 volts. So whether I go through the top loop or through the bottom loop, in both cases, 12 plus 12 volts is dropped. So both loops drop 24 volts. And Kirchhoff's laws are good there. This next example has 2 batteries, so it's a little bit more complicated. I'm going to solve it the same way, which is I want 3 equations to solve for 3 unknown currents. And again, I'm going to use one node, and then I'm going to use 2 loops in the circuit. This circuit has 3 possible loops. I'm going to choose the 2 loops that only have 1 battery through the loop. So first I'll start off with a node, and that'll be right here. This node has I1 coming into it from the top, and I2 coming into it from the left. And then coming out below it is going to be I3. So current in, I1 plus I2 equals current out, I3. And that's my first equation. Rearranging gives that. Now I need to choose a loop. So I want to keep 1 battery in the loop, so I'm going to do first this outer loop, which comes from the battery and then through 30 ohm resistor and the 20 ohm resistor. So starting from the battery, I gain 20 volts. Then I lose some volts here. And again, by Ohm's law, that is 30 I1. And voltage is resistance times current. And then I go all the way down to the 20 ohm resistor. So that's going to be a voltage of 20 times I3 lost. And that equals 0. And rearranging the equation gives that. Now to make things easier, I'm going to choose the bottom loop. For the bottom loop, I start at the 10 volt battery, gain 10 volts in the battery, lose 5 I2 volts in the resistor, and then I go through I3 again and lose 20 I3 volts in I3, and that goes to 0. I'll clean that up in a bit. The other loop I could have done is this top loop here, which involved both batteries. This one would be a little bit more complicated because the batteries face opposite directions. So if I wanted to do Kirchhoff's laws, I would have to reverse the signs because I'm sort of going through this branch here in the middle backwards. So I would have 20 minus 30 I1, and then minus 5 I2 plus 10. So the signs would get reversed. Just to make things easier, I chose the two loops with only one battery. So the bottom loop gave me that equation, and solving that equation gives those currents there.